and I have the great pleasure and privilege in introducing all of them. And let me first start by introducing the first speaker, Professor Caslav Brukner. Of course, Professor Brukner doesn't need any introduction, but for the benefit of young students and others who are here, I would just say a few lines. So Professor Brukner is the scientific director of the Institute of Quantum Optics and Quantum Information, Vienna, and he leads the Quantum Foundations and Quantum Information Theory group at QIQT23. And he's, of course, a professor at the University of Vienna and a distinguished visiting research chair at the Perimeter Institute. He holds several positions, visiting positions. He also holds distinguished visiting full professorship at the International Institute of Physics in Natal, Brazil. And his research interests lie in the areas of quantum reference frames, quantum physics on indefinite causal structures, quantum physics related to gravitation and general relativity, then also other areas like reconstruction of quantum theory, quantum to classical transition, and quantum communication complexity, Bell's inequalities, macroscopic entanglement, so on and so forth. And he had made a number of very stimulating, original, and path-breaking, contributions and ideas to these subjects. And today he will speak on the subject of quantum reference frames from foundations to applications. And without further ado, I would request Professor Brukner to please start your talk.
Thank you very much. It is a great pleasure to be here and very nice to see many people present. I also want to thank you for a nice introduction. So as you mentioned, one of the main focuses of our research group is quantum reference frames. I don't know how much you're familiar with these objects, but what I will thought today to introduce the notion of quantum reference frames as we use it in our group, and then apply this to a very specific problem that has been open and discussed very much in the last decades, and that's the definition of a qubit in the relativistic quantum physics, more precisely in definition of relativistic spin. So there are many other aspects of quantum reference frames that I will omit for today, and I will concentrate on this specific problem based on some more general theory that is specified in this first Nature Communication paper from 2019. And then what I will talk after introducing this concept as in this paper, I'll talk about relativistic spin qubit as in these two papers. The reason I have chosen this is very much related on how we process information at relativistic speeds. So the problem of the spin in special relativity is very large, very old. There have been zillions of proposals how the spin should be defined in special relativity. And the reason for this ambiguity is that there is no well-defined separation of the angular momentum and spin, like in a non-relativistic quantum physics. And more precisely, there is certain coupling between the spin and momenta for relativistic particles that make difficult just to think about Hilbert space of a two-dimensional system like a spin 1/2 in non-relativistic case. And I will list a couple of papers here that have been in which the spin definition has been considered, starting from 48, but also more recent paper. I will not talk about any of them very particular, but this series of work should give you an impression that the problem is persistent and there is no consensus on how we should define a spin in special relativistic situations. And maybe the most influential paper is the one which I flashed now at the last, and it's a paper which I put in the red box. It's a paper by Asher Perez, Petra Scudo, and Daniel Terno, that really introduced this problem now more than 20 years ago in a paper written in quantum information terms, and I read here a very short abstract. We consider single free spin 1/2 particle. The reduced density matrix for its spin is not covariant under Lorentz transformation. The spin entropy is not a relativistic scalar and has no invariant meaning. Now, when you read this paper or abstract, I'm sorry, then you see that what has been proven reduces very much usage of a spin as a prime example of a two-dimensional Hilbert space. And you may wonder whether we can really consider the spin 1/2 particle in special relativity as a qubit, because if the entropy of this spin is not invariant, then we may lose information just due to a movement of the particle without really interacting the spin with some environment around. So how should we encode or decode information in a qubit if you use the angular momentum of a relativistic particle is the question that I want to pose for this time. And in order to address this question, I will need to introduce the notion of quantum reference frames. And I hope I will convince you that there is a solution and there is no loss of information and there is a well-defined way how we should encode and decode qubit in relativistic particles by the end of my talk. So here is the outline of my talk. I will first introduce, just briefly remind you on classical reference frames transformation, and then I will introduce the notion of the quantum reference frames and the transformations. And then I will talk about something which colloquially could be called superposition of translations and boosts. And then I take the notion of the quantum rest frame, and this will allow finally to address the initial problem of relativistic spin qubit, and also to show that those particles, if entangled, can also maximally violate Bell's inequalities, hence showing that there is no loss of relative resources for our quantum communication tasks. And finally, I will conclude. Now, let me introduce classical reference frames transformation through two explicit examples. What you see here, and I hope you see also my cursor, we have a passive interpretation of translations. We have a system in certain quantum state psi in unprimed reference frame, and then we look at this system in a prime reference frame, which is shifted by some distance x0. Then the way how we connect the two states in the two reference frame is through this unitary transformation, which encodes translations in space, with the P being the generator of translations and with x0 being the parameter of this transformation. Another also well-known example from the textbooks is the boost. And here I talk about non-relativistic boost, Galilean boost, in which I want to connect the two states of the same system described in two reference frames that move with respect to each other with a constant uniform velocity v. And then the connection between two states is again given through the unitary transformation, where now the generator of the Galilean boost is given by this combination of p and x observables, and the parameter of the boost is the relative velocity. Now, if we think about reference frames in general, physically, in experiment, in our laboratory, reference frames are always physical systems. So we usually make then statements like the system, for example, is 10 meters away from something which is physical object, from the tree, like in this situation. Or maybe this tree is on some platform together with the system and moves with respect to some prime reference frames. But again, even these prime reference frames or the origin of this reference frame is associated with some physical object. Now, if you think that reference frames are real physical systems, then they themselves should obey physical laws. In particular, they should also obey quantum mechanical laws. And although it's a bit absurd to think about macroscopic objects like trees being in a superposition, at least in principle, we can think about these situations in which the platforms or the origin of our reference frame associate to the system that ultimately obey quantum mechanical laws. And therefore, the previous situation with two trees and one quantum system can be seen as a situation in which maybe from prime reference frame C, both the old reference, unprime reference frame A, and the system B are in some joint quantum mechanical state. And then again, we can ask ourselves how I can describe the change of the description of my quantum mechanical system B if I move from one to another reference frame, with the important difference that now the reference frames with respect to each other are in some quantum mechanical state. And of course, although this is a very intriguing and idea, it remains open how to formalize this idea of quantum reference frames. And that's what I want to do next on, again, an explicit example of translations. Ultimately, I will move then to the boosts to define the relativistic spin operator, but let's try to be very simple at the beginning and think about translations as the most simple, maybe, group of transformations. So what you see here are three particles. And one of the particles in each of these two figures has a flag. This particle that has a flag will count as an origin of the reference frame. So on the left-hand side, you see a blue particle as an origin with respect which I define the distances to the orange and the gray particle. On the right-hand side, the reference frame has changed and the orange particle takes the role of the origin with respect to which blue and gray has corresponding coordinates. Now we see that these coordinates change from left to right by mere fact that we change the beginning of the reference frames. In particular, the B particle has now the relative distance to the A particle. And now we want to think about this very trivial situation in quantum mechanical terms. Now, what we have suggested back in 2019, that there is nothing particular quantum classical at that level of description. And as long as the particles are localized, well localized in space, we can well put the cats around these positions and states. And in that way, generate transformations between quantum mechanical states. And then, of course, we can ask ourselves how we can get from the left-hand side, set of basis sets on the left-hand side, the set of basis sets on the right-hand side. Again, I denote that the C on the left and A on the right are just non-dynamical reference frames. I include sometimes them in the description, like here explicitly, but I can also exclude them because for all the time and for all situations, they keep being at the 0 point. They do not change. So either we include them explicitly or exclude them, but you should remember that all the bases that I am talking about previously are bases between A and B on the left-hand side and C and B on the right-hand side. And so we may ask whether this set of states and that set of states are related and what is the relation. And in order to explain the relation between these two sets of states, I introduce here in the second line an operator that can be divided in two parts. One concerns the shift of the B, and we see that the B particle is shifted by the generator, which is a momentum B particle, for the amount where A particle is. That's the connection between these two. And then there is a blue part of the transformation which concerns interchange of the states between C and A, because we move from the C reference frame to A reference frame. So what we have at the beginning is 0xa, and we get minus xa 0. So the transformation that does this is something which we call parity swap. It mirrors first xa and then swap C and A system. And then these two operations combined are the transformations that change from one to another quantum reference frame. And this combined is a composition of two unitaries, one being conditional phase shift. You see that here at XA, I don't have a parameter anymore when I want to shift B, but I first look where A is, conditional where A is, I shift the B. And the second part that just exchange the role of AC, taking into account this mirror symmetry from XA to minus XA. So that's, after all, the unitary transformation between that transforms C into A perspective. Now, how we can apply this? And let's apply on some examples. Here's an example where C and A reference frame are very well localized, and only quantum particle B is in a generally non-local state. Now, nothing particular changed. This is a situation which we usually do have in our laboratory because we don't treat reference frame as quantum. They are localized in space, and then we know how to change the perspective of looking at the B. The real interesting situation appears when one of the reference frame, let's say the new one in which we will jump, so to say, is already in the superposition of two localized states. What happens then under the influence of this unitary transformation is that once I jump on A, the two other particles become quantum mechanically correlated. And this could be intuitively understood because if in the original system I'm in this shadowed orange, then I'm close to C and far away from gray than if I'm in this strong orange point where I'm then further away from C and closer to gray. And this corresponds exactly to these correlations that formally can be written in terms of an entangled state. So that's the initial state. We jump at the A reference frame, which is a superscript always. And then in this superscript, we localize A, sorry, in this new reference frame, we localize A, but C and B become entangled because the B will be shifted by the amount that depends where A is. So that's why this exponent depends on XA1 and here XA2. So indeed, this is an entangled state. And of course, as I said, this can be obtained by acting this operator on the initial state. So what we learn from that is something very strange, namely that superposition and entanglement are notions that are relative to quantum reference frames. As long as we consider classical reference frame transformation, this is not true. But now, because the reference frames themselves can be in quantum mechanical states, this becomes a relative notion. And here are some examples of what I just told you. One of them being something which we already mentioned. That's the case when both C and A are well localized. Well, then nothing dramatically changed from jumping from C to A. Then another case is something which we just discussed here. We said the new reference frame will be in a superposition of two localized states. So when I jump in A, the C and B will be entangled, as we just saw. And this left lower corner figure is the situation that is opposite from the one just discussed. Here we start in the original reference frame C into entangled state such that A, B are correlated in space. We don't know where A is, but we know that wherever A is, B is at a constant distance, L from A. So when I jump on A, B will factorize out. It will be exactly the distance L, but C that was localized will become delocalized. So again, we have a notion that entanglement and superposition are reference frame dependent. And the last right lower figure is a continuous version of what I just said and can be applied on EPR state, but since it's physically the same, I will not go into it. Now, all what we have now introduced is the idea of quantum reference frames for translations but it can easily be now extended to other groups. And here I will, from now on, talk about quantum boosts, or instead of quantum translations. So I will talk about a very similar situation in which I have initial reference frame, and then the new reference frame moves with respect to the initial one in superposition of velocities. And what I want then is somehow to jump on the rest frame, if you want, of this new reference frame A, and to look how then description of C and B changes. So we have a transformation between two quantum reference frames, which are in a superposition of uniform relative motions with respect to each other. And then what happens is that this transformation is actually very similar in form as the one we previously introduced, with important difference and similarities in that is a composition of two unitary transformation. Again, the first one is exponential representation of unitary of the boost, but with the important change that besides the generator of the boost, which acts on the quantum mechanical system B, instead of parameter that used to be velocity, is now an operator that acts on system A. So what this operator does is reads out what the velocity of A is, and then correspondingly performs the boost of particle B depending on this velocity. And the last part of this transformation concerns only exchange of the perspectives between C and A, such that if I had velocity of A, then I will have the same velocity of C, but over the opposite sign. Just as similarly as we had this mirror transformation for the position in the case of translations. So basically, the form is always of this composition of two unitaries, one conditional transformation B, and then exchange of the roles of A and C. If we do perform this, then our previous situation that we described as some state of B and superposition of velocities or moment of A under the introduced transformation changes into something where A is now in the rest frame, but the B and C get again entangled because how much the B will be boosted depends on the velocity of the C. So for every velocity of C, I will boost differently B, and that's why I get entanglement. Okay, now I want to go into basically an example, which is very instructive, but doesn't provide any new knowledge that you have not had before. But it should demonstrate that the idea of quantum reference frame is not just a speculation, but it also gives back the results that we may expect otherwise, and maybe we have alternative ways also to compute them. And then I will go to the real problem, and namely to the relativistic speed. So the question is how we can move to the rest frame. Now, obviously, it's very easy to move to the rest frame if the system or if the system moves with a definite velocity. We know how to move. We just move with the same velocity, and that will be the rest frame. But what would mean to move in the rest frame if the system itself is in a superposition of different velocities? So here is an example of what I want to say. Imagine that we have a problem which is well studied in atomic physics, namely that we have an atom that moves with certain velocity towards an incoming photon, and we want to find out what is the maximal probability for transition from ground to excited state. What is the transition frequency? Well, if the transition frequency in the rest frame is omega b, then the Doppler shift induced tells us that we should tune the photon frequency through this Doppler shift such that the photon frequency matches this omega b, which was the transition frequency rest frame, times 1 minus velocity of the atom divided by c. And now we have the problem. If we go beyond this simple situation and imagine that we have an atom which moves in a superposition of two velocities, we may ask ourselves how we should prepare the state of a photon and atom, again, to have a maximal transition probability. How should we match the transition to the, how should we prepare the frequency of the photon and the whole composite system of photon and atom if atom is not moving with a well-defined velocity? Obviously, we can match one of them, but not both, seemingly. It seems something like that. Now, the solution that we want to suggest is the solution with the quantum reference frame. Namely, we say, let's move in the rest frame. In the rest frame, we know what is the transition frequency. That's the one that we introduced before. We solve there the problem. We have the probability transition maximized, and then we can move back in the lab frame and find out what the state should be performed in for the photon and atom. So here is pictorial what I mean. If we move from the previous situation, where the atom was in a superposition, into the rest frame of the atom, well, in this rest frame of the atom, the laboratory itself will be in a superposition. Although this is not something which we need to prepare, this is just a point of view that we can, in our thoughts, take as if we were sitting on an atom. That will be the description. In other words, if I'm sitting in the rest frame of the atom, then there are 3 degrees of freedom that I can describe in the following way. There is laboratory, that's the laboratory state. Then there is one photonic state with some frequency. And then there is a ground state of internal degrees of freedom of the atom. And I know how large this frequency must be. That's exactly the transition frequency in the rest frame to maximize the probability that the ground states go to excited state in the rest frame of the atom. Now, in this rest frame, laboratory is some superposition of all possible velocities or momenta. And so we wrote here all this huge superposition of all possible momenta. And we also introduced some time evolution for the free evolution of the laboratory. Now, if I want to go from this reference frame in my laboratory reference frame, I should perform a transformation from one quantum reference frame to another. So in the relational reference frame, in the rest frame of atom, the C, B, and A tilde were degrees of freedom. And in a new reference frame, now A tilde, and B are degrees of freedom. It's an external degrees of atom, internal degrees of atom, and the photon. And as you see, I omitted now the rest frame in the description because this will be always at 0, and I didn't write it here. And so now if I go from atom's reference frame into the lab reference frame, and I start in the atom's rest frame with this state, apply this transformation, what I get is indeed entangled state. So this is pictorial picture is or description of this entangled state. But what actually happens is that I have an entangled state such that for every momentum or velocity of the atom, I need conditionally to shift, Doppler shift. So this state in this reference frame looks as a huge entangled state over all possible momenta, but such that whenever I have momentum PA, I must correspondingly Doppler shift the frequency of the atom to have the maximal transition amplitude, or to have the maximization of getting the excited state. And this is something which we might even expect without the machinery of quantum reference frame. Yes, if atom is not in well-defined velocity, then the best way is to prepare an entangled state between a photon and an atom, such that for every velocity of an atom, we Doppler shift the frequency of atom, and then we will maximize for each of these momentum the transition probability. Okay, now I go back to the problem that we had at the beginning and ask myself, can this machinery answer what is the spin in special relativity, and also explain the paper by Paris, Kuda, and Turner? So let me just remind you what is the spin in non-relativistic physics. It's defined operationally through the Stern-Gerlach experiment. So we have a spin, we have a magnetic field, we have a deflection of the spin in an inhomogeneous magnetic field, and we operationally define spin for low velocities in that way. And we introduce spin or Pauli operators, spin operators along 3 different directions. Now, if I have if I have a relativistic particle, well, then in order to have something what was spin up in non-relativistic low velocity case, in order to again be deflected with probability up, probability 1 up, I need to rotate my magnetic field. So the alignment of the magnetic depends on the momentum of the particle. For each momentum, I would need to align magnet different, and this comes from the fact that the relativistic boost actually couples momentum and spin. So if I start with a state of momentum and spin in the rest frame, where energy momentum vector is like that, where the velocities are almost 0, when I have only the rest energy, and I have some spin, then out of this state, if I apply on this state a relativistic boost, then this relativistic boost will change these states in a new state in which I will have some non-zero momentum, but also spin direction will depend on this momentum. And the nice way to see this is the spin operator actually depends on gamma and beta, where in both of them we have the velocity of the particle or the boost with which we change the state. So we see that there is some kind of a coupling between the spin momentum, which as long as the momentum is well defined, is not a problematic, because whatever the spin is, as long as it's well defined, we will orient the magnet correspondingly, and the results will be the same as in a non-relativistic case. We will have 3 possible directions for the spin, and we can nicely define our qubit. But what happens if the particle is not in well-defined momenta, but is in a state of superpositional momenta? Then obviously no definite magnet orientation will return our full qubit space. And so what we instead suggest that for the state of a general state, that indeed in which we have a coupling between momentum of the spin, so it's a most general state with some invariant integration measure, we suggest that to measure the spin in this state, we do the following. We move to the rest frame of this particle that moves in a superpositional momenta. There we measure the spin with the help of the standard Stern-Gerlach experiment, and then we move back to the lab frame and find out what should we measure in the lab frame to get the same statistics as the statistic of the spin measurement in the rest frame. And of course, this pictorial means that if I have, for example, a particle that moves in a superposition 2 velocities, then I know that the spin depends, orientational spin depends on the velocity. So I do have something like that, some entanglement between the external degrees of freedom and internal degrees of freedom. But then what I expect is that when I go into the rest frame, I will have a well-defined momentum spin orientation, but then the price to pay it is that the probability will be in state of superposition in the opposite direction. And so let's now formalize this. I start with the rest frame of a particle in which there is a well-defined separation between the laboratory and my spin, and velocity is 0. And the laboratory is, of course, then the price to pay is in a superposition of the momenta. Now, what I do is, again, as I have done for the Galilean boost, namely, I introduced quantum reference length transformation that is, again, composition of two transformations, one which is the Lorentz boost. This Lorentz boost acts on the spin, but it corresponds to the velocity of the laboratory. So I first read out what is the velocity of the laboratory, then correspondingly rotate the spin. And the second part is just exchange of the velocities between A and C, between the laboratory and the particle. And so now what happens is, if I apply this transformation on my initial state in the rest frame, what I will get, if it was a product state between definite momentum of the laboratory and some spin orientation, then I will get that my particle moves with the same velocity in the opposite direction, but my spin will be oriented differently. Namely, it will be rotated dependent on what was the momentum of the laboratory. And this, again, is connected, as we said, through the Lorentz boost. Now, this, just to repeat, this like parity swap ensures that the velocity of the two objects, namely the laboratory and particle, is opposite. And now, if I start with something of that form, where I introduce that laboratory doesn't have a well-defined momentum, as in this is just to see action on one basis, but is in a superposition of momenta, this transform that in the laboratory frame in entanglement between momentum and spin orientation for the particle now seen from the laboratory frame. So we have indeed entanglement. And whenever we have a product states in a rest frame, we have entangled state in the laboratory frame. And now, not only the states can be transformed, also operators can be transformed. With this quantum reference frame transformation, we can operationally identify a spin operator which gives the same results as in the laboratory frame, which gives the same results in the laboratory frame as the one in the rest frame. And in the rest frame, for example, we have, when we measure just spin and don't measure momentum of the particle, then we measure just spin operator on the spin degrees of freedom. But now this corresponds to the in the laboratory frame to the operator that transforms as any operator from one reference frame to another with this unitary transformation sandwiching the original operator. What we obtain in this way is, for those who are familiar with spin operators, is Foldy-Wothuysen or Price spin operator in that way, but here justified through the quantum reference frame transformations. And now this operator is the one which we claim should be measured in the laboratory frame. This operator has a very nice correct non-relativistic limit because it's basically the same operator on the spin and it's just exchange between C and A. So in the non-relativistic limit, it boils down to the Pauli or spin operators. Without going into the limit for any possible velocities, we have the same SU2 algebra as the spin operator. So in that sense, they are not distinguishable from the algebraic point of view from the spin operators. And finally, it has a correct eigenvalues. It has the same eigenvalues, well, spin up and spin down, or plus or minus 1, or plus h bar half and minus h bar half, because we need to transform both, of course, states and operators, and then these transform operators act on the states in the laboratory frame, returning the same correct eigenvalues. And so we can now conclude that what this operator means, these sigma operators, They act on the whole Hilbert space, both on momentum and spin. But for the spin 1/2, they have only 2 possible eigenvalues. So they are hugely degenerative operators on the spin momentum. And they can be identified with certain partitions of the total Hilbert space. Namely, we have a partition of the Hilbert space of all states of that form, where I have spin down in the rest frame and any possible state of laboratory. When I transform this, I will get a set of the states that all should be corresponding to spin down or to the result spin down, but it's of course hugely non-generative subspace. And then I have another one, which can be obtained by applying this quantum reference frame transformation on spin up in the rest frame, and then transforming to the laboratory frame. All those states will return spin up. So it's again just 2 eigenvalues. So we can effectively treat the relativistic spin as a qubit with the help of reference frames, in which we now defined what are the observables we need to measure in the laboratory frame to return the same algebra and to have the full coding and encoding of qubit in entire Hilbert space of momentum and spin. Now I'm almost at the end of my talk. We started a little bit later, so I have just 2 slides. I didn't go into the details how this quantum reference frames transformation now applied for the relativistic spin can help us doing certain quantum communication tasks. And let's assume that this task is violation of Bell inequalities, which we know is relevant both for communication complexity or for the quantum key distribution and so on. The idea is that now we have 2 entangled relativistic particles. And we wonder what measurements we need to perform on Alice and Bob side such that we restore maximal violation of Bell inequalities. It has been shown in many papers that if we measure just spin by a usual Stein-Gerlach magnet, we will lose violation, we will lose quantum features of this, or we will overlook or not measure the proper observables, and the violation of Bell inequalities can decrease and can even decrease to the level that is below the classical bound, and therefore we might think that we have no resources in our labs. The ideal quantum reference frame is help us to restore and to revise this problem and to see that there is an appropriate observable to measure in Alice and Bob laboratory such that violation is again maximal. And the idea boils down to the following. What you see here in the upper picture are 3 systems. There is C, which is laboratory, A is one particle, B is the other particle. And what we suggest is to start the problem already in the rest frame of one of the particles. So in this rest frame of one of the particles, we know what should we measure to measure spin and not lose any information. Well, we should just measure sigma, which is the spin part without momentum part. But in this rest frame of a particle, not only that laboratory could be in some superposition, it could also be, for a more general quantum states, that the B particle is already in some superposition between the velocities and orientation of spin. But now if you compare this picture of green and red, this is exactly the picture that where we consider only the single system from the laboratory frame. We said single system could be in some strange state, which is entangled between momentum and spin, like in a red particle, and the green particle was our laboratory. And then we say, we know what we need to measure here. We need to measure this large sigma operator. Then I will not lose any information. And this large sigma operator will measure both momentum and spin. So situation of the two particles is which both moves in a superposition of relativistic momenta, is similar to the situation we previously considered in the laboratory in a single particle, because once we jump into the rest frame of one of the particles, the other one is in a more general state, for which we know how to measure the spin or what preserves the spin algebra. This is this large sigma operator. So in the rest frame of A, we measure this operator, which is Pauli sigma or spin operators, non-relativistic, so to say, on A side, and this quantum reference frame transformation induced sigma on the B side. And this, when we measure, we will see that we can maximally violate Bell inequalities in the rest frame of A. And then the lower picture is going from the rest frame of A in the original laboratory frame. And now the laboratory is localized. It's just this big origin of reference frame C. And in this laboratory frame, then the green particle is in a superposition of velocities. And for each velocity, the spin is rotated differently. But furthermore, for each this full line, not this kind of light fuzzy or diffused, for each full line, I have also the full line correlations. So for this state of the green particle, I have correspondingly Lorentz boost, initial velocity, initial spin and velocity of the B particle. Okay, it was in the rest frame 2 of them, so I have to have 2 of them. And for the other velocity of the particle, this dashed one or light one, I have another dashed line pair of states that are now Lorentz boost for the velocity of A. So in that way, we go back and know exactly what we can measure and how the state look like in the laboratory frame, such that we do not lose any information and can achieve maximal relation of Bell inequalities. So if I may conclude with a cartoon, what we suggest is that if we are in some laboratory and the particles are non-relativistic, almost velocity 0, then we know how to measure the Bell's inequalities. We have the maximal relation for the usual setting for the spin. If the particles move with relativistic speed, but we still use just in laboratory frame these spin measurements, well, we will lose some correlations. So from maximal correlation, we go to the low correlations because the spin entangled state on each side will get spins and correlated with momenta. And when we trace out the momenta, which would mean perform the measurement only in the spin part, we will lose correlations. However, if we succeed to move with the particles, and that's why it's a little bit strange, this fuzzy picture, namely for every possible velocity of left and right particle, we move our measurement apparatus with them, then we will effectively in these new reference frames perform the first measurement in the rest frame of these two particles and therefore have maximal relation. So with this, I would like to conclude. I first try to motivate quantum reference frames as taking seriously the reference frames are physical, and furthermore, that as such, they need to obey quantum mechanical laws. I also want to emphasize that we don't need really to be observers in these reference frames. We can, what we very often think, we put ourselves in thoughts as being in a specific reference frame, not necessarily physically there. We perform in these reference frames computations because they are easier to perform in this reference frame, and then we go back in the reference frames in which we do perform measurements and are physical. Then one consequence of quantum reference frames was that superposition and entanglement are frame-dependent notions. and that we can have generalization of symmetries, of which I didn't talk about much, but generalization of transformation of quantum reference frames through the superposition of space translation boosts. And finally, there is an interesting notion of quantum res frame that allows us to define a relativistic point operator satisfying the spin algebra and enabling maximal evaluation of Gauss inequalities any quantum relativistic frame. And with this, I would like to thank for your attention.
Yeah, thank you very much, Professor Brukner, for this very nice talk. So now yes, please. Yeah.
Yes, I would turn on my, okay.
Yes, yeah, we can see you now. So now this is open for questions. So if anybody, let me also see the chat box. If there's anything, there's nothing. So while we wait for some question, let me just ask you maybe a very sort of silly question. So as you showed very beautifully that if one is able to go to the rest frame of the particle, then you can, you can overcome the effects of normal loss of, say, entanglement. But so for example, for photons, there is no rest frame one can go. And also for other particles, if suppose one is not able to exactly go to the rest frame, so has there been any study based on your work which can show to the extent we can overcome this degradation of correlations, even if we are not able to exactly go to the rest frame, but maybe we can achieve some velocity here. Have I made my question clear, or is it kind of?
Yes, I think that it's a very interesting question of how this can extend to massless particle, and I have no answer to that. This is something which bothers me as well. At least this formalism cannot help us to answer what we should measure in the laboratory frame. And I do. The second question, I think, is about precision. And indeed, if you do not if you cannot match the velocities perfectly, or you cannot go into the rest frame, or you cannot measure exactly these observables that are combined observables between the spin and momentum, you will have loss of coherence. And I think from the practical point of view, it will be very hard to measure what we suggest. We should somehow maybe filter coherently all momenta, and then for any momenta move our magnetic field correspondingly to get the full observables, but this could be very hard in practice.
Yeah,
it's actually an entangling measurement between spin and momentum.
Yeah, that's sort of tricky. I suppose it's
yes.
But anyway, it's a very, very nice approach, and at least in principle, we can understand through your approach. I mean, what really happens when this relativistic transformations are, why do they lead to the loss of coherence?
Exactly, because
that was a question which was there till a long time.
That was a question, and it is really kind of tension, because the boost is a unitary transformation, and so you do not expect that you lose any coherence. But of course you don't know where this information is, and then I think our approach helps to trace where the information went, and if experiment allows also to catch this information and use
it. Yeah. So that will be, very interesting indeed. And the other sort of, application, which I just naively thought perhaps, is of your formalism, maybe to also not just look at entanglement, but sort of other correlations, like these days. Also for a long time, there's a lot of activity in prepare and measure scenarios, where you do not need really entanglement, but you build up correlations in time. So there also, relativistic effects can degrade your correlations, and in this respect, your method or your formalism may help towards mitigating the loss of coherence.
I think it's very kind of universal. It's really related only to the moving to the rest frame. So I guess also in other scenarios where relativistic speeds are relevant. I have picked up this application for the reason that it's relevant for defining the qubit in relativistic physics. But we do see application of quantum reference frames in other areas, not necessarily quantum information. For example, when we want to describe gravitational field of source by quantum particles, which is, of course, something which goes into the direction of quantum gravity, and it's a very hard problem. And there is no aim or even ability to go and solve this problem in full. But there are specific scenarios, thought experiments, that through the quantum reference frames can help us address properly. And this is the idea that you have a large mass in a superposition. According to the general relativity, this large mass curves space-time. But of course, the space-time is not well defined then, because the particle itself is in a superposition. You can have some kind of superposition of space-time, whatever it means. And now you can think about, if I have this large mass in a superposition, then I have a pro-particle, how this pro-particle would fall into the gravitational field of this large mass in a superposition. And then you can take many different assumptions to solve this problem, even approximately. But what we want to suggest instead is to say that, well, quantum physical laws are invariant on the change of reference frame, even in a change of quantum reference frames. So how about we take a reference frame in which we are standing on this large mass in a superposition, if you want. So this large mass is then localized, and the gravitational field is well defined. Well, then pro-particle that maybe was localized before will be delocalized. But this we know how to solve. This is a particle, quantum particle falling in a well-defined gravitational field. So we don't have a problem which is inherent for quantum gravity, that the space-time is not well defined in this reference frame. And then we say, okay, then let's solve this problem in this reference frame, and then go back. And that will be the solution.
Yeah. So this approach is, works there as well. Yeah. So thank you. And let us see if there is any question.
Can I ask a question?
Yeah, please go ahead. Yeah.
Yes, please.
Yes. Thank you for your talk. When you apply translation operator on the wave function, then do you see spread of the wave function at translated distance?
Do we see the spread of the? So this transformation is for any state. So, or if you want, for if there is dynamic for any moment of the of dynamics, we can make translation from one. We can make transformation from one to another reference frame. So if you induced what I want, spread of the wave function in one reference frame, you will see the spread of in the other reference frame. If you ask, for example, just let's say two particles in the whole universe, and one is spread wave packet, then what I would, this is a more difficult question that you pose, it's more interesting. I would say that if you jump on the other particle, this will be conceived as a spread of a wave function of the first reference frame. So we have particle 1 and 2, and I have a spread of particle 2 as seen from 1. And then I would say, if I jump on 2, I will see the same spread of particle 1. And now the next question of you could be, but come on, if the mass are different, the spreads are not the same. Yeah. And that's a very fundamental question. And I will argue that if there are only two particles in the whole universe, there is only one mass. This mass is a relative mass. And this maybe can be seen if you consider really two particle systems, but you consider only relative degrees of freedom. That's when there are two particles, that's only the relative distance between them is relevant. And in the relative distance, degree of freedom is a relative mass that enters. And that's why the spread is the same. Mm-hmm. That's a very deep question, and more complicated situation, not easy to answer, and we don't have an answer.
Yeah. It may ultimately impact will be on the localization and then also on the entanglement degree.
Yes.
So, thank you.
Welcome.
Thank you. So is there any other question? So if not, let us thank Professor Brukner once again for